The transactions observed in the rotational spectra. For the transition J is equal to 0 and J is equal to 0 to J is equal to 1. In that case, Ej is equal to h by 8 pi square Ic into J plus 1. It is a rotational energy level. If we substitute J is equal to 0, then at that time Ej is equal to 0, it gives, if we substitute J is equal to 0, then E0 is equal to 0. If we substitute J is equal to 1, therefore E1 is equal to h by 8 pi square Ic is nothing but the B. If we substitute B and 1 into 1 plus 1, it gives 2B. Therefore delta Ej for the transaction J is equal to 0 to J is equal to 1, in that case Ej is equal to 1 minus Ej0, E1 minus E0 is equal to 2B minus 0 is equal to 2B centimeter inverse. Position of the first line in the spectra for the transaction J is equal to 0 to J is equal to 1. This is allowed transaction. Second one, for the transaction J is equal to 1 to J is equal to 2. J is equal to 1 to J is equal to 2. Delta Ej is equal to E2 minus E1. If we substitute J is equal to 2, in that case E2 is equal to 6B. If we substitute J is equal to 1, in that case E1 is equal to 2B. Therefore 6B minus 2B, it gives 4B centimeter minus inverse. It gives the position of the second line in this spectrum for the transaction J is equal to 1 to J is equal to 2. This is allowed transaction. Next, for transaction J is equal to 2 to J is equal to 3, delta Ej is equal to Ej is equal to 3 minus Ej is equal to 2, where J is equal to 3, which is equal to B into 3 into 3 plus 1, 4 into 3, 12. It gives 12B. For J is equal to 2, E2 is equal to 6B. If we subtract E3 minus E2, it gives 6B minus centimeter minus inverse, centimeter minus 1 or centimeter inverse. It gives the position of the third line in the spectra for the transaction J is equal to 2 to J is equal to 3. Since the allowed rotational energies are given, which is equal to B into J plus 1, or B is nothing but the rotational constant h by 8 pi square Ic. The wave number of the different rotational level will be 0, 2B, 6B, 12B, 20B, 30B, and so on and so on. And for two adjacent rotational state, the energy difference is given by delta Ej is equal to Ej plus 1 minus Ej, which is equal to 2B into J plus 1, is equal to 2B into J plus 1 centimeter inverse. Hence the wave number of the lines observed in the rotational spectra, wave number of the lines observed in the rotational spectra will be 2B, 4B, 6B, 8B centimeter inverse and so on. From this allowed transactions, we can conclude that the various lines in the rotational spectra will be equally spaced, and they are separated between, or the separation between two lines is 2B. All lines are equally spaced and the separation between these lines are 2B. Okay, any doubt in this? Just try to find out the energy levels of a rigid diatomic molecule for J is equal to 0 to 6. we know the formula Ej is equal to B into J plus 1. Just substitute the value of J is equal to 0, then find out E0 is equal to 0. Substitute J is equal to 1, then E1 is equal to 2B. Substitute the value of E is equal to 2, you will get E2 is equal to 6B, and so on and so on. From which allowed transactions, which transactions are allowed, that I discussed in previous slide. Okay. Now if we see the allowed transaction, all the lines are equally spaced. If j is equal to 0 to j is equal to 1, it gives 2b line. Next, j is equal to 1 to j is equal to 2, it gives 4b line. J is equal to 2 to j is equal to 3, it gives 6b line, and so on. All these lines are 2b, 4b, 6b, 8b, 10b, 12b, 14b are equally spaced. And the separation between two successive lines is 2b, and it belongs to a microwave region. So the separation between adjacent line is equal to 2b. So b can be obtained from the spacing between rotational lines. So one example of rotational spectra of a rigid diatomic molecule, that is HCl. Absorption versus wave number. This is line separation in the rotational spectra of HCl. Line separation between the rotational spectra of HCl is 21.2 centimeter inverse. Then we have to find out B. For that, moment of inertia of HCl is equal to mu r naught square. So m1 m2 divided by m1 plus m2, mu is nothing but a reduced mass, which is equal to m1 into m2 divided by m1 plus m2. If we find out that value and substitute in this equation, b is equal to h by 8 pi square IC, then we get b is equal to 10.6 centimeter inverse. You have to find out the value of rotational spectra, and that value can match with this value, b is equal to 10.6 centimeter inverse. Now today you have to find out reduced mass of HCl, then bond length. Using that bond length, we can find out moment of inertia of diatomic molecule, substitute that value and find out B. This is your homework. Similarly, rotational spectra of CO. If we see this transmission versus wave number, J is equal to 3 to 4, J is equal to 4 to 5, J is equal to 5 to 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. All these transactions are allowed transactions. In that case, change in energy is delta Ej is equal to 15.3 centimeter inverse, 19.1 centimeter inverse, 22.9 centimeter inverse, 26.7 centimeter inverse, 30.6 centimeter inverse, 34.4 centimeter inverse, 38.2 centimeter inverse. Actually, this work This observation was done by Mitchell Halls in modern spectroscopy in 1992. Okay, the same formula we have to use, that is Ej is equal to B into J plus 1, where B is nothing but the rotational constant. Next, some numerical problems. We have to discuss some numerical problem related with this concept. The first rotation line in the rotational spectra of CO is observed at 3.84 centimeter inverse. Calculate the rotational constant B and the bond length of CO. The relative atomic weight of C is 12 and O is 15.99. Then absolute mass of H is 1.67 into 10 to the power of minus 27 kg. So, how to find out a rotational constant and bond length? So, here wave number for the first rotational line, that is 0 to 1 transition, which is equal to 3.8424, 3.84235. We know transition between 0 to 1, it gives wave number is equal to 2b, and that 2b is equal to 3.8425. Therefore, b is equal to 3.8425 divided by 2, which is equal to 1.9211 centimeter inverse. Means easily we can get a rotational constant B is equal to 1.92118 centimeter inverse. Now, the next aim is to find out the bond length. So, first I is we can find out moment of inertia, h by 8 pi square B.Sc. We know the value of h, b and c. If we substitute all that value, we get moment of inertia of CO is equal to 6.626 into 10 to the power of minus 34 divided by 8 pi square into 2.9979 into 10 to the power of 10 into b. The value of b is 1.92118. If we substitute that value and simplify, we get moment of inertia is equal to 14.5695 into 10 to the power of minus 47 kg per meter square, kg per meter square. Now, moment of inertia is nothing but the mu r naught square, where mu is nothing but the reduced mass, which is equal to 19 point, which is equal to m1 m2 divided by m1 plus m2. If we substitute the value of m1 m2, finally we get moment of inertia, reduced mass is equal to 11.38 kg. Now, r square is equal to I divided by mu. We know the value of I, we know the value of mu. If we substitute that, which is it gives 1.279 into 10 to the power of minus 20 meter square. But we have to find out r. Taking square root on both sides, r is, and then we get r is equal to 0.113 into 10 to the power of minus 9 meter, or 1.13 into 10 to 1.13 Armstrong. In this way, we can find out a rotational constant, its moment of inertia, or a bond length by using above equations. Okay, such kind of numericals can be asked in university exam also. So, be prepared. Any doubt in this? If you have doubt related with this rotational constant, bond length and moment of inertia, you can ask me anytime. Just try to solve this numerical problem again and again. So thank you. Remaining part we will discuss in next lecture.